So good morning everyone, this is lecture number 29 E524 Digital MOS LSI Circuits, and today is October 29, 2020. So we were studying sequential circuits in which we have studied static latches and flip-flops. Also we have studied dynamic latches and flip-flop. In dynamic latches and flip-flop, our major concern was the 0-0 overlap, or maybe the 1-1 overlap. To remove this, we have used overlapping clocks. We also understand that C-square MOS technique is better one to isolate both the stages, right? So C-square MOS latches we have studied. Other than that, also we have studied pulse resistors, where it's the same class of C-square MOS latch, but instead of giving the clock and clock bar, you are giving clock and clock G, which is the glitch circuitry. And after that, we also studied sense amplifier based resistor. In a sense amplifier, right? So we have studied this circuit where we also used these two PMOS to make sure that it's pre-charged to the level where we want, right? So okay, this is in and in bar. So when there is in is going from, first of all, it's depending on what is the value of clock. If clock equal to 0, both the outputs are 1 1 because they are connected to VDD. So when clock equal to 0, outputs are connected to VDD, and it's going to latch the previous value as per the this latch circuitry. And at that time, because these are VDD, these two transistors which are on top are going to be off, and these two transistors are going to be on. So that is what going to happen, right? And during that time, because of this VDD, the point over here are actually connected to VDD minus VTN, right? And when there is clock equal to 1, when clock equal to 1, these will be removed, and when clock equal to 1, it's evaluate mode, and clock equal to 0, it's pre-charge, or it latches the previous value, right? So during clock equal to 1, this is what going to happen, like this is connected to ground, and at that time when in equal to 0 to 1, and this is going from 1 to 0, what is going to happen over here? So because this is going from 0 to 1, later stage this is going to be on, or you can say this will be shorted, and this will be removed. So this particular node is acting as a high impedance node, right? When it's going from 0 to 1, in that case this particular node goes to 0 because of this one, because of 0 resistance path. So because of this one it's 0, and because of this connection which is connected to VDD, it will make this connection and this also becomes 0. Otherwise, if you don't keep this one, then other part will be VDD minus VTN, because this was earlier connected to VDD and other side will go to VDD minus VTN, and the whole thing is acting in such a way that one side is VDD and one side will flip to 0, and that will make the other side going in a differential mode, right? So that is what we have studied, and because of adding this one, this makes sure that this is a resistor. Otherwise, if you don't keep this one, then output will change with respect to changes of in and in bar. Notably, in and in bar has to be differential in our case. Okay, so this is what we have studied. Now, next part is the pipelining, and what we exactly want to do. We want to increase the speed, but if you want to increase the speed, the thing is you need to increase W by L, right? If you increase this, it will decrease resistance and increase capacitance, right? So this way we are increasing the power consumption. I want to see everything at low power, means speed has to be very high and power has to be low compared to what we are doing with the speed. So this is what I want, but unfortunately, as per the science which we have developed, actually it's not possible. So what is possible thing is, I'll give you one example. Let's assume that there is a place where there is a fire. Okay, so there is a fire over here, and one place where there is well where water is available. So there is a big water tank, you can say, and there are 100 buckets are there. So such 100 buckets are there, but I am alone. So when I'm going here, like going here and then going there with one bucket, it required lots of energy from my side, right? Because everything has been given to me. So in that case, what we can do, instead of this, let's assume that there are 100 people are there like me. Each one of them has one bucket. So each one of them are going there and coming back. Still look, fire will be removed, it will be removed, but the problem is one guy will again like he has to consume lots of energy to going from here to there and there to here. Look, in between lots of water will be also leaking, right? So better thing might be, let's assume that we have 100 people and 100 buckets. So if I keep such kind of people in between with, so 100 people are there, and let's assume that I'm standing here, the first one. So I go here, get the water, and I give this bucket to the next guy, and this guy gives bucket to the next guy. After 100 passing, you can see that last guy will get the bucket, the first bucket. But during that time, I'll not be standing and just watching that whether 100 passes happen or not. I'm going to take the second bucket. I'll fill it up and I'll pass it to the next guy. So what is going to happen over here? You can say that after 100 passes, this flow of the buckets are continuous. So from here to here, when I'm passing it, if there are 100 passes, right? So after 100 passes, the last guy will keep on sending the water to the fire, right? By the way, such kind of popular thing is known as the bucket brigade. This is a very popular concept. If you know how the fireman is the like many fireworks together work using the bucket brigade concept, right? So they have the pipe, they are holding together, right? And then wherever the fire is, they are sending the water, right? In that case, so if one guy is doing this, it's not possible. Look, it's very heavy and it's not possible to do that. But this whole concept is bucket brigade, where different passes will be there. So one guy is going to have one bucket after one pass. Second guy will have after second pass. But after having 100 passes, everybody will have 100 buckets. And thereafter, like keep on sending the water to other side. But the first 100 passes are the one when fire didn't get any water, right? So this basically known as the pipeline structure, where what we are doing from, let's say, wherever you have input, and the other side is output. You know that between inputs, or maybe let's say inputs and outputs, you might have different arithmetic units, or maybe some latches and flip-flop. All those things require three things. One is called setup time, one is called hold time, and one is called the propagation delay. That might be like PCQ, right? So we have to manage all these things, and accordingly we have to decide the clock. Sometimes system clock, and from system clock you are deriving different phases of clock. So that has to be more than what is listed over here. When actually it's nowadays jitter is also playing important role, right? Because you're going very high speed, so jitter will be there. So in that case, the regular way, if you are doing this, like there is a one complete block, it might be like, let's say, arithmetic logic unit, addition, multiplication, and all these things, and along with that I want to run it at particular clock. Then that clock has to be faster than what I require for setup time, hold time, and all these things, right? So you can understand this whole thing is actually problematic for creating a good clock. And because of this clock, which is coming from PLL or maybe oscillators, so that requires load, lots of load, it consumes lots of power, and at the end of the day, like you have to drive it to ALU, where there is not only one place where this clock is going, but there are inside this, there are many places where this clock is going. So clock load is going to be increased, right? So it's, and for running output at such a high speed, you need to have WL very high, right? Like this is general concept. So in that case, if you are increasing it, capacitive load is going to be increased, resistance is decreased, of course, but other things are going to be coming with the like, it's not only the positive things are coming, but there are lots of negative parts which are coming because of this. So what I can do, I know that most of the time this ALU does not work or it's in active mode. I need to find out what is the thing which is active. What I mean to say is as follows. Let's assume that you have two input NAND gate. You might have four input NAND gate. Generally, when you are writing a Verilog code, it generally choose like two or three input AND gate or maybe four input AND gate, but we don't take 32 or 64 input NAND gate, right? What exactly it does inside? Okay. Can you see? So four input NAND gate is like this. So if there are four inputs A, B, C, D, A, B, C, D. Look, this particular NAND gate is not going to work until I have output A0, O0. And this NAND gate does not work until I don't have the output O1. O0 is only available after the propagation delay of first NAND gate. O2 is available after the propagation delay of DP1 and DP2 both. And before that, if something is coming, even though it's a combinational logic, it does not act. Or with the TP3, you're going to have the third one. But instead of doing this, if I do as follows, like this is also a very simple thing. Right? Because the time when this was computing, at that time another NAND gate will also compute, right? So I have to find out the way that which particular function has to be done in parallel, and if it is not working in parallel at that time, maybe you can make the sync such a way that these values are stored in registers. Notably, these registers are dynamic one or maybe static one, and they are operated on alternate basis. Means afterwards you might have some different function also, so that all those things are running in parallel or in also in cascade. Such thing is known as the pipelining. So let's go to the book. What it says. It says that pipelining is a popular design technique often used to accelerate operation of the data paths in a digital processor. The idea is explicitly example whatever they have taken. In that they want to compute log mod of a minus b. So this is what they want, log a minus b. If I want to do that, what I can do, first of all, I'm going to take minus of a and b. Then I'm going to use a module where it takes the modulus of whatever a minus b is coming, and afterward I'm going to take the log of whatever I got, and then there is an output which is log mod of a minus b. Note that when I'm doing this, the whole thing will take propagation delay of all these blocks, right? And right now I'm showing that this is just a combination logic. It might be clock or it's operated on clock. Then you might get all these things with the fact that setup time, hold time, and maybe the contamination delay all has to be checked for each of them, and accordingly clock has to be decided. So this is what it's saying over here, that where both A and B are presenting streaming of numbers. That is, computation must be performed on a large set of input values. And note that A and B are the variables and they are not the fixed value. It might be the stream of numbers, means it might be changing like 001100. It's changing. See, and it's coming to this particular channel serial. So continuously there is stream of some number, something like this, and so on. Does not stop here. So output has to be, it's not a static value. It's value which is changing with each clock. So you need to use a resistor which is storing the value at a given clock, and then you can perform the rest of the things. And in that case you have to make sure that this clock has to be much higher than setup time, hold time, and the contamination delay. So that is one of the challenging tasks, because you have to take care of all of them together, which is written over here, that clock period has to be combination of all such things, which is already known to us, that this first one is the contamination delay, second is the setup time, and PD logic is the one which is the worst case delay path through the combination and adder, which consists of adder, absolute value, logarithmic, all these things. And it's all these things depends on what technology and other things you are using, right? So in that case the solution might be, instead of doing this as we were doing earlier, and as we have decided that we are going to use the pipelining, what I can do at the end of the each of the operation, add one resistor which might be positive or negative age triggered, but you are going to keep, if this is clock, I'm going to keep clock bar, if this is clock bar, this is clock, and this is clock bar. What it does actually, the output here is available after, maybe it requires, as we have done over here, we required 100 passes for this one. The output was coming after 100 passes. So this also requires some sort of clocks, and thereafter the output is available. So whatever the, look, there is, it's not a, I would say that it's not a delay, but it's also kind of delay, but after this particular time the output is continuous, means till that time when these clocks are passing the output is not coming. That is known as the latency. Latency is output with respect to time, and latency is measured in terms of clocks. So output is late by so many clocks, right? And once that clock is available, or all these things are done at that time, output is available continuously. But note that when this output is available, or maybe when this output was not available, the first clock, this guy was processing the data. In the next clock, this guy is processing the data. In the next one, this one is. So after 3 consecutive clocks, this is going to happen. And note that when you are doing this clock and clock bar, it's not, I'm not making the positive age triggered only, but because of this one, this is actually working as like positive and negative. In that case, the requirement of the clocks are actually half. You can take next clock also if you wish, like every positive age triggered, this is going to be activated. Like if I do the first clock, this is going to take the data. Second positive age trigger, it's again going to take data. So that is possible. But in that case, what is going to happen? This guy is going to interact with this guy. Means there is a direct connection. If A is available over here, let's say, and B is available over here at clock, and the output is available after propagation delay. So clock plus some propagation delay of logic, output is available here, but still clock is high, right? So if I have designed the resistor such a way that it's working at clock with the hold time little bit higher than what is here, if I did that, then this data is transparent for this resistor. So it's not a correct way to take the clock. It's better to take clock bar so that it saves the clock, as well as it will not allow this data to pass. This data will be passed when next clock is coming in a negative side. So going from positive side, this is going to take the data. Negative, this is going to be rephrased, right? So that there is no clashing of data. So clock and clock bar, that is going to we are going to do over here. You can see here. So this is the okay. This was the traditional way where clock and clock have been kept, but in pipelining we are adding everywhere different resistors having the clock, right? So there are various ways, like you can do with the clock and clock bar, which is saving the time, or you can take as it has been kept over here. So the first clock, and it's going from 1 to 0, sorry, 0 to 1. At that time, let's assume that A has given 1, B has given 1. So that data will be available over here, right? And it will do the operation of minus maybe. And output of this one is A minus B. But this is happening after, this A and B get the A minus B after the propagation delay of both the blocks. When this is available here, note that I am not going to make this data is not going to be available at the next side, because I'm making sure that this whole time of this resistor is much smaller than this propagation delay, right? So the whole time of this one is here, let's say, and the output of this one is coming afterwards. So then it will not be taken. But if you are making this whole time of this resistor somewhere here, then this data will go that side, right? Because there is a transition from 0 to 1. So we have to make sure that, otherwise this thing will be problematic. So if whole time of this resistor is much lesser than I would say that the whole propagation delay plus hold time or the contamination delay, all these things of combination of both resistor as well as the ALU. So in that case, this is not going to take the faulty input, or you can say that output of each one of them might be 0 if you have made it such a way that they are 0. Sometimes some people are also keeping it VDD. VDD means they have they have used a resistor which is going to precharge the value, right? Like we have did it in sense amplifier based resistor. If you are using sense amplifier based resistor or something like that, then this value will be VDD, because when there is a clock, it's VDD, or it will latch the previous value. Right now there is no other previous values available, so I may reset it, or maybe I can recharge it, right? So any one of the thing I can do. So I'm assuming that you are going with that. So the first clock has not taken the data, but when there is a second clock, so in that time this data is available, much before this clock is going again from 0 to 1. So in that case, in second clock, this A minus B will be transferred over here. Notably, when there is a second clock, at that time, next data, let's assume that it's 0, 0. I'm assuming just number. Next data is 0, 0 is available. So in that case, these values will updated, right? Some new values are there, and accordingly A minus B will be here. So this is the updated number, but we again made this valid that t hold time of this register is much lesser than maybe TPD plus t hold and all other things. Then this 0 will not going that side and will not erase what was happened in the previous one, right? So it will give this data, and again this particular data will get the modulus of two numbers, and then whatever is the propagation delay, same thing is valid over here while designing the register of this particular diagram. Then this data will also not go to that side. This cannot go here, right? Because it came much later after the clock is changed from 0 to 1. However, when there is third clock, at that time this data is available, and that's going to be given at the next side, and after log value, that log value is available over here, and it's going to be hold with the fact that t hold is much lower than, by the way, this hold is belongs to the resistor, by the way, and plus. So with that valid thing, this is not going to take the data. However, this data will be transferred to the output when there is the fourth clock. When there is fourth clock, output is available. Till the fourth clock, output is whatever output is there, it's invalid, right? So output is coming only after this one. Let's call this one as valid out. And after that, every clock means, if you look at the fifth clock, I would say that I would start with the first. After fourth clock, whatever the first number was here, that got the whole operation like log of mod A minus B. So that is available with the first two data after fourth clock. Right? Fifth clock is the one which is going to give you the next data. And again, like it's continuous streaming, right? So this is what happening, and every time this data has to be stored somewhere, otherwise it's going to be erased, right? So such thing is known as the pipeline, and same thing we can apply to many other things which we have studied previously. By the way, same concept is also used in designing pipeline ADC. If you are interested to know the pipeline ADC, you can go to my lecture in mixed signal VLSI design, where this is not the data which is working on digital side, but the input is analog and output is digital. All these resistors are going to give you the data which is in 1 and 0. So okay, so as I was telling you, you might have the pipelining, like one function is f, one function is g. It might be anything, like f is AND function. Two functions, I want to use it like using a pipeline, and I know that the function f is important, or you can say that G is a function of maybe F, right? So in that case, if F is available, then G will give the output. So in that case, we are using such kind of pipeline thing. Here, as you know, it's a dynamic thing. So I'm using the clock, capacitor, and NOT gate. Clock, capacitor on and NOT gate. Same thing which we have done it for the dynamic latches and flip-flops, right? So in this case, whatever is there in F, by the way, note that this is a static function. I can use dynamic also if I wish to use, but that might be the advanced one. But at the beginning, when you are starting, let's assume that at clock I want to evaluate this function, and this particular function, if I am using with the combination logic, which was the chapter number 6, which we have already studied. So using any of the technique, if you are implementing that, that consumes power most of the time, because it's a static power. There is a, like, it's either of the side, it's connected to VDD or ground. And in dynamic, you can use it and you can reduce the power if you want to do that. But the whole thing is working with the clock. I suggest to combine both of them together, and you can have some function or some circuitry which is going to give you better output. I mean to say that better output means, look, in such kind of thing, let's assume that if 0 0 overlap is occurred, if it is 0 0, then in that case, okay, 0 0 will make sure that all these transistors are off, so there is no data is moving here and there. But it creates a problem when it's an overlap of 1 1. If 1 1 is overlap, all the transistors are NMOS. In that case, all the transistors are on. So output is available immediately, whatever the value is there. But we have to take care that there is whole chain is available right now. And because of that, you might have some malfunction output, which is not your requirement, right? In that case, what to do? In that case, if you remember, we have studied something called reverse conduction. When you have implemented these switches with transmission gate, if you remember this, in that case also such things were happening, right? So in that case, we have like used two things. One was, the NOT gate like this, which is weaker one, but still that particular technique, weaker one, is not going to save what I want to do, right? So what I can do, there is another technique which is famously known as C-square MOS. How does C-square MOS look like? This is same thing what we have already studied, but for you people, I'm drawing it one more time. So this is the C-square MOS based flip-flop. Okay, so if rest of the things, like when it's going from 0 and like clock equal to 0, clock bar equal to 1, what is going to happen, it's already known to us. The thing is, when it's 0 0, that is also known to us, but for your information, I am just going to make it here. So if there is 0 0 overlap, what is going to happen? clock equal to 0, this is equal to 0, and clock bar is also equal to 0, right? In that case, what is going to happen? Look at the different transistors. So this is going to be on, this is going to be on, right? And at that time, these two transistors are off, right? So look at that. If D equal to 0, or rather, let's take D equal to 1. If D equal to 1, then this particular transistor is also off. So it will be the previously latched value. On the parasitic capacitor over here. But when this D is not equal to 1 but D equal to 0, then it will make this connection on. Because of this on connection, this is VDD. If this is VDD, this transistor is going to be on and this transistor is going to be off. In that case, what is going to happen? This particular node charged to VDD, and this particular node will be, because of this transistor, this is going to be 0, right? So even if there is overlap, the output is actually what you wanted, right? And similarly, like you can take the case when it's 1-1 overlap, it will be reverse of what we have done, right? So upper part will be close, and accordingly you will have the output. So in this case, if there is overlap is there, one guy is not going to affect. Sorry, there is one mistake over here. It's as good as, so output is previous one, so that was a mistake, sorry. So D is not equal to out when there is 0-0 overlap, right? But when it's absolutely either clock equal to 0 and clock bar equal to 1, the output will be the one which you want, right? So that is what happened over here. However, in the case of the reverse one, which is 1-1, let's try that one also. Let's assume that clock and clock bar are having the 1-1 overlap. If it is 1-1, clock equal to 1, clock equal to 1, clock bar equal to 1, clock bar equal to 1, all are 1, because there is overlap of 1-1. In that case, all the NMOS are going to be on. This is on, this is on. At the same time, these will be off, right? Now the whole thing is depending on what value of input we are giving. So if D is equal to 0, then this transistor is, this node is not going to be VDD, it will be the previously latched value. And similarly, output is also previously latched value. Whatever is there, it will be staying there. And when D equal to 0, of course, this transistor makes the connection. However, this side is high impedance node, and there is not a complete circuit, so that VDD can be going over here. But when D equal to 1, then the lower transistor is again on. It makes a connection here to 0. Because of 0, this transistor makes the connection. However, because of the high impedance node over here, this D value does not transmit to the output, right? So that is what we have learned in C-square MOS. latch or flip-flop, you can say. This is one of the solution for the case when there is clock skew. Now you must be knowing what is the meaning of clock skew. Clock skew is the one when clocks are getting overlapped, right? So during that time, if such things are happening, the solution, the base solution might be the C-square MOS latch or maybe flip-flop, whichever you want. Latch is the level sensitive and flip-flop is the age trigger, right? So I was talking about the previous solution, and here if same thing is happening, let's assume that.
Sir, I have one question.
Yeah.
When clock is zero, then there will be no input. Then at that state, how F is computing that time?
When clock equal to 0,
there is no input coming, then F is how is computing function F.
yeah, so it's not computing, it's computing only at 1.
But it is written on the waveform, it compute F when clock is zero.
Oh, okay. I need to see whether it's corresponding to this waveform or not. Right? Your point is valid. Yes. Computation has to, or might be the thing that after having clock equal to 1, F is created such a way that which is not shown over here. This is the possible thing that when clock bar is there, F is going to be computed. This might be the possible thing. So that one guy is not disturbing other one. That might be the possible thing. I'm not sure, but I copied from Rabe book. So what is the text written in between? I need to check. Okay. So, okay. So, but main crux of the story is if there is a clock skew or there is a like direct path going from in to out, means if clock and clock bar both are equal to 1, means 1 overlap. 0 does not make sense. However, if you are using the transmission gate, in both the cases 0 and 1 overlap, it creates a problem, right? So in that case, one simple thing is use non-overlapping clocks. So what I mean to say, for such structure, the easiest solution might be to not do anything, just make like this. Right? So during this time where this yellow color has been shown, where both are 0 0, so if both are 0 0, there is no direct path from input to output, right? So this solution is known as non-overlapping clocks. So rather than what has been used over here, we can use this structure to avoid the problem. This is the easiest one. But let's assume that you are not using only in with maybe this particular transistor. The reason is in might be 1 or 0. Okay, anything it will be there. So 0 can transfer strongly 0 other side. However, if there is minus VTN, as already known goes, and if you are using PMOS, it can transfer 1, but it does not transfer 0 efficiently. So one solution might be like you are using the transmission gate. Okay. Right? That is possible thing. Or you can do one thing, you can use one more circuit which is latching the output and it's restore the level, right, which you want. So that is also possible thing. But I am not talking about all these things. Like if you are not interested in all those schemes and you are like you want to take the situation when all the clocks are having the 1 overlap, then in the worst case you can use C-square MOS latch. And using that, by the way, there is one more word which I already told you, but let's repeat that word because sometimes people has doubt. When there is a 1-1 overlap and input is available at output or output changes with respect to input, that particular condition is known as race around condition. Or simply you can say that there is race. So if there is a race between input and output, in that case, we need to use solution which is C square MOS latch, and that thing we are going to known as NORA CMOS logic. NORA is no race around condition. So there is no race around when you are using this particular thing in a computing for the pipeline structure. Look, we are talking about the pipeline. Maybe